The Java.lang package is kind of special. For one thing, you never have to mention it on an import statement. It's as if every Java source file began with this import statement. But it's more than just a package of classes and interfaces that you can use in your program. Well, it is that too, but parts of the Java.lang package are part of the Java language. Nothing demonstrates this better than the string class. The language has built-in operators just to manipulate objects of this class. These two statements result in the same object being created. The reason is that anytime you place a quoted string of characters in your code, the compiler generates a command to instantiate a new string object. That alone makes it a part of the language, but there's more. Look at these two statements. The first one creates a string reference named x and assigns a value to it. On the right side of the equal sign, two string objects are first created, then a third string object is created by concatenating the two together. Finally, it's the address of this third string object that's assigned to the reference. In the second statement, the string object on the right side of the equal sign is combined with x to form a third string, and this new string is then assigned to x. So string objects are very much a part of the language. I should note that the processes I just described are what conceptually happens. In reality, optimization simplifies those steps. There is a lot of optimization done in Java. It's one of the things that makes modern Java so fast. This statement causes the value of the variable y, whatever it is, to be converted into a string and then treated like one for the rest of the statement. Anything in Java, variable, object, constant, anything, will automatically be converted to a string when added to another string. All this makes the string class an integral part of the language. The Java.lang package contains some classes that can be used as wrappers for all the fundamental types. They're all capable of containing a value of the specified type, and they all have methods that can be used to return that value in various forms. There is one that doesn't contain anything. The void class can be convenient as a placeholder when you have a collection of various types. You're familiar with the math class and its elementary functions for exponentials, logarithms, square roots, trigonometry, and so on. The strict math class is the same thing, but it was compiled with strict FP, so it's more portable. The original math class is more accurate, but the results may vary a bit from one platform to another. Use strict math only if portability is an issue. It gives exactly the same results on all platforms. The interface and the class that makes multiple threading possible are part of the Java.lang package. I'll have some examples of using both of them in a later lesson. In the next lesson, we take a look at the annotation sub-package of the Java.lang package. The annotation package contains items to help in adding annotations to your code. You've already seen how annotations are added to your code. This lesson is about some of the annotation tools available to you. The retention policy enumerated type contains three named values. The value source causes the annotation to be discarded by the compiler. It exists only in the source code. In effect, it is no different than a normal comment. The class value indicates that the annotation is to be retained by the compiler and put into the class file, but it will not load when the class file runs. It will not be available at runtime. The runtime selection causes the annotation to be retained in such a way that it is available inside the running version of the class. The retention annotation contains only one value, the value of a retention policy. If you don't specify a retention, it defaults to the class value. That means that about the only time you will use one of these is to specify runtime to make the annotation available programmatically. Another enumerated type is the element type. It specifies the type of thing the annotation is to be applied to. Now, this value indicates that the annotation will be applied to a class, interface, enumerated type, or to another annotation. You can also attach an annotation to a package declaration, a constructor, a field value, a local variable, a method, or a parameter. You specify the element type by using a target annotation. If you don't specify the type, the selection of the type is automatic. If you specify a target type other than the one actually present, it's a compiler error. Now, there are only a couple of more. You've already seen an example of using documented. It will cause the following annotation to be included by java.doc. Here's one you haven't seen. If you mark an annotation as inherited and you use that annotation on a class, the annotation is inherited by all the subclasses of that class as long as they have no annotations of their own. There is more coming about annotations in a future lesson, but the next lesson is taking a look at the structure and the purpose of the java.lang.instrument package. The facilities of the java.lang.instrument package can be used to write a program called an agent that monitors and reports on another program running inside the same Java virtual machine. This is the simple Java program that I'm going to apply a simple instrument to. It's a variation of the Hello World program. All it does is print out the one line showing the glyph that is the character 6. When you run it, it prints one line of code like this. What we want to do is to be able to get a hold of the byte codes of the class before it executes and change them in some way. To monitor a program, it's usually a matter of inserting trace commands into the bytecode. You can do it in any of 1,000 ways. You can put in breakpoints, counters, tracers that let you know when the code executes, insert method calls, or even completely replace some code. There's no limit to what you can do, but for this demonstration, I'm just going to change the character 6 to a 7 after the class loads, but before it executes. To do that, I need to create an agent. This is the simple agent we're going to use to monitor the program. It starts with a pre-main method instead of a main method. It's called pre-main because it executes before the main method of the program we're going to modify. Notice this first parameter. It's not an array of strings. It's a single string. All the command line arguments come in as a single string, and you'll need to break the string apart if you want to get to the arguments. The second parameter is a class giving you access to instrumentation. You can do anything you want to in pre-main. Anything that you could do in a main method can also be done in pre-main. That includes creating objects and starting threads. In this simple example, nothing is done except a transformer program is added to the instrumentation. The transformer program has the job of modifying, called transforming, the bytecodes of the class. Here is the transformer I wrote for this demonstration. It implements the interface class file transformer. The interface requires one method, transform. The transform method does the job of editing the bytecodes. The transform method of every registered transformer is called once for every class that's loaded. The return value of the method is an array of bytes. There is a bit of a terminology problem here. The class file is the loaded form of the class. It is in memory, not on disk, but it's still called a class file. Now the first argument is the class loader that was used to load the class that is to be transformed. This is the fully qualified name of the class. In the agent, you can call the redefined method for the instrumentation object to have an already loaded class redefined, and if so, this will be the class object of it. This is the protection domain of the class, and this is the class itself. These are the bytecodes that are to be transformed. The very first thing to happen is to make sure that this is the class that we want to transform. If not, just return null. That's the same as returning with no transformation of the byte values. This for loop executes once for each byte in the class file. All the bytes are output to the screen just for this demonstration. Now here's where the transformation takes place. If this byte is the character 6, it is replaced with a 7. Finally, the size of the class is output and the array of bytes is returned. Now, in the real world, you would want to edit the bytecodes, but that can get pretty complicated, and I won't go into the format of a class file here. That could take up the rest of the course. An agent program is stored in a jar file. This simple script can be used to compile the classes and build a jar file. The jar file contains both the agent and the transformer. The manifest of the jar file specifies which class is to be run as an agent. Now you have two ways to start your agent. You can start it when you start the program running, or you can configure your agent to attach itself to a running program. Which way it works is defined in the manifest file. For this demo, I'm going to start the agent on the same command line that runs the program, so the agent has a pre-main method and is specified as the pre-main class. This is the command to run the program and the agent. Notice how the command begins and ends. It's a regular command to run a program with one option in the middle. The option names the jar as the agent. When it runs, the translation takes place. You can see the 6 has become a 7. Needless to say, there is a lot more to instrumentation, but this gives you the basic structure so you can get started. By the way, it's easy to let the documentation confuse you about this package. In the Sun documentation, the word instrument is used as a verb. They talk about software that instruments a program. In the next lesson, we look into some things that you can do to interact with the garbage collector. This lesson is about how your program can monitor garbage collection. When your program instantiates an object, Java grabs a block of free memory and initializes it for you. When your program is through with it, all it has to do is clear all references to it, and it becomes available for the garbage collector to grab the memory and put it back into the freely available space. This all works very well, and over the years has gotten so fast that we hardly pay any attention to it. But circumstances can arise where you need to do something special. With a little work, you can use all that free space. Imagine a situation where you have thousands of objects filling memory, and when some free space is needed, the garbage collector comes and gets what it needs and notifies you about what has been recycled. That can be done using the classes of java.lang.ref. Normally, when you create an object, you store its address in a reference, which is a pointer. You can get to the object directly. It's said to be strongly reachable and will not be recycled by the garbage collector. If you no longer have the address of an object stored anywhere, it becomes unreachable and is subject to immediate garbage collection. With the java.lang.ref package, there are 3 ways you can store the address of an object in such a way that the garbage collector can come and get it, and you'll be notified that it did. You can create a soft reference to hold your reference value, The soft reference class will accept your reference as the argument to its constructor. The garbage collector will come and get it if necessary, and you will know about it when you try to retrieve it. If the return value is null, then the garbage collector got it. You can make the object that you store in a soft reference as large and complex as you wish. As long as you have no strong references to any part of it, it may be collected. But you have to be sure to remove your other references because the garbage collector knows all and sees all. And you can find out what the garbage collector knows. Let's say you have an object that you're using in a number of places, and you want to check and see whether all the references to it are gone. The garbage collector keeps track of such things, so that information is somewhere inside the Java virtual machine. You can get to that information by using a reference queue and a weak reference. You set it up by creating a weak reference containing the object you want to monitor and a reference queue object. Then a call to the remove method will block until all references to the object have been deleted. Then it will return the address of the weak reference object. These are the soft and weak references, and there's one more, the phantom reference. You can use it to determine whether an object is about to be reclaimed. You use it the same way you would use a weak reference, but once an object is phantom referable, it cannot be reclaimed. The finalize method will have already been called, so you can never get it back. In the next lesson, discovering inside information about loaded classes. The java.lang.reflect package makes it possible for you to obtain information about the public methods and variable definitions of loaded classes. The reason the package has the name it does is that Java calls this reflective information. It was originally intended for use by debuggers, interpreters, and class browsers. Every object in a Java program has a class object along with it. Now, this class object holds all the definitions of variables, methods, and constructors that make up the object. To get a copy of this object, it is only necessary to call the getClass method, and every object has one. The examples in this lesson call the getClass method of the current object, but you can do it with any object you can address. Here is a class with a couple of fields defined in it. Notice that they are defined as public. Reflection only works with public items. This example starts out by creating a new object of this class. Then it gets the class definition of the object it just created. The class object has a getFields method that returns an array of field objects, one for each variable defined in the class. This loop prints out the string produced by each of the field objects. It prints out a complete descriptive list of each variable. The field object has some other methods, including one to retrieve any annotations attached to it. It has methods you can use to both get and set the value of the variable inside a specified object. Using this same process, you can get a list of all the public methods. It is only necessary to call getMethods, and it returns an array of method objects. Notice this class has the public method sum defined for it, but it returns the names of a few methods other than just sum. The two methods defined in this class are shown as would be expected. These other methods are all inherited from the superclass. Notice that the names of all the methods are fully defined so you can tell where they are defined. There are several other method calls available. You can get the parameters and return value types. You can even execute the method through the method object. Here is almost the same example again, but this time it implements a couple of interfaces, and it gets a list of all the implemented interfaces. Now the interfaces are returned described in class objects, and you can do the same thing with this class object that you do with any class object. You can get the names of the methods and variables if you want them. This example does about the same thing as the previous examples. It just lists the names of the interfaces implemented. One last example. Now you may have noticed that the listing of the method names did not include the constructors. They are handled separately. This class only has one constructor, so the array returns with a single constructor. We are able to get an int value with bits set for all the characteristics of the constructor. The modifier class has a number of static methods that can be used to determine the meaning of these bits. This example prints one line for each modifier bit, which describes all the characteristics of the constructor. Alright, that's a quick look at reflection. The next lesson is about management of the Java virtual machine and the computer's operating system. You can monitor the way the Java virtual machine handles memory. Now, different Java virtual machines will handle memory a little differently. Generally, though, the JVM divides memory into two parts. The part you're more familiar with is called heap. It's from this portion of memory that space is allocated to load classes and instantiate objects. This is where the garbage collector does its work of reclaiming memory for reuse. The JVM itself, along with variables and methods shared by more than one thread, are not stored in the heap. Now actually, what is heap and what is non-heap will vary from one JVM to another, and on some systems, some garbage collection is done in parts of the non-heap area. A Java virtual machine can have more than one memory manager working with the same area at the same time. The garbage collector is just one type of memory manager. It's possible for memory managers to appear and disappear while programs are running. This class demonstrates the collection of memory information and the results of invoking the garbage collector. Now this class contains one variable, a string reference. At the very beginning, the show method is called to display the memory information. Then this loop executes, concatenating 1,000 strings into one large string. Without garbage collection, the result is that 1,000 small strings and one huge string are left in memory. No garbage collection takes place during this loop because not all the available memory is being used. Then the memory information is shown. The reference is set to null and the memory information is shown again. The show method displays the memory information on one line. The management factory class has a static method that returns a memory MX bean object. Then this call gets an object containing all of the memory information. There is also a method called getNonHeap memory information. With the JVM I'm using here, it doesn't change, so I left it off. You might want to try it. Your JVM could be a little different. Anyway, the committed memory is the amount of memory that has been committed for the heap for use by the JVM. It is immediately available. The init value is the amount of memory that the JVM first requested from the operating system. The max is the maximum total memory that can be used by this JVM. The used memory is the most interesting one for this demo. It's the amount of memory that is actually being used. Here's what it looks like when it runs. Here at the very beginning, no strings have been allocated yet. This is what happens when the strings are allocated in the heap memory. And this is after the string reference has been set to null. No garbage collection has taken place because the JVM did not find it necessary to do so. That is, garbage collection does not take place right away. It only happens when memory is needed. In this example, GC was called to force garbage collection, so the amount of used memory went to a minimum. By the way, some of the numbers like max and committed could show up as -1 to indicate that the numbers don't mean anything in your system. You might want to play with the numbers in this example. In particular, things start to vary quite a bit when you allocate a lot more strings. You can have your program look outside the Java virtual machine and find out what hardware and operating system your program is running on. The management factory is used again. By the way, the reason a factory is used instead of a regular constructor is that there is only one of these objects. Each time you call a factory method, you get the same object. Anyway, you get an operating system mxbean object, and it contains the information. You call the various methods of that object to get the information. This gives you the architecture, the number of processors, the operating system, and its version number. All that's pretty clear, but that last one, the system load, is not so clear-cut. It's the average of the load per processor over the last minute. The way in which this number is calculated is system-dependent. So if the load number is important to your program, you will need to experiment and check with the number over a period of time. And there's more. You can find out much more about the operating system environment through other objects that you can get from the management factory. Class loading information includes the total number of classes ever loaded, the number unloaded, and the number currently loaded. Some Java code is compiled into native code by the JIT, the just-in-time compiler, before it is executed. You can find out how much time is used in this compiling. You can find out all about the JVM system, its name, version, specification version, start time, uptime. You can find out the class path it uses to locate classes, its library path, and even the command line arguments that were used to start it running. You can get information on threads and even detect deadlocks. You can check on the CPU time used by each thread, and you can get the history on the number of threads used since the JVM was started. You can check on locks, blocks, and suspensions. You can find out the thread ID numbers and names. There is even more you can do. If you need to get into the system in any way, check the facilities of the management factory. This was the last lesson on the Java.lang package. In the next lesson, we'll begin looking into the Java util package.